Welcome to Still Science Lab. Tonight, we explore a strange truth hidden inside the night sky. Space looks open, infinite, and full of promise. But the deeper physics looks, the more the universe begins to feel like a trap that makes the stars almost unreachable. Stand beneath a clear sky, and the stars do not look impossible. They look suspended above us, distant but present, separated by darkness yet close enough for imagination. Their light enters the eye. Their names fit inside human language. Their patterns have guided travelers, shaped myths, inspired science, and carried the old feeling that the universe is something we might one day cross. From the ground, the stars feel like invitations. But light is deceptive in a quiet way. It can bring the universe to us without making the universe reachable. A star can send a photon across the void, and that tiny messenger can arrive at Earth after years, centuries, or thousands of years of travel. We receive it, name the star, measure its color, estimate its distance, and feel, for a moment, that we have touched something beyond the world. But seeing is not reaching. Knowing is not crossing. The night sky collapses distance into beauty. Physics restores the distance. And the distance is almost beyond the scale of life. Space is often described as freedom. It is the final frontier, the open dark beyond the atmosphere, the place where the imagination escapes Earth's surface. There are no walls in space, no ceiling, no locked gate. No visible border where the universe says stop. It seems like the opposite of a prison. But a prison does not need bars if the distances are large enough. A trap does not need walls if escape demands more time, energy, endurance, and technology than any living species can easily command. Space does not trap us by enclosing us tightly. It traps us by being too vast. It offers endless direction, but almost no accessible destination. It gives us a sky full of lights, while placing those lights behind gulfs so large that the human mind can barely hold them. That is the first paradox. The universe looks open, but it functions as separation. Earth may feel small when viewed against the stars, a fragile planet, one world among billions, a pale island orbiting an ordinary star. But compared with the emptiness between stars, Earth is not small in the emotional sense. It is dense with everything space lacks: air, pressure, warmth, oceans, soil, gravity, shielding, chemistry, life, sound, weather, memory, a horizon close enough to walk toward. Earth is not merely where we happen to be. It is the environment our bodies were written for. The rest of space is not naturally waiting for us. It is not a larger version of Earth with more room. It is almost the opposite of a habitat. It is vacuum, radiation, cold, heat, silence, distance, and time. To survive there, humans must carry pieces of Earth with them. Air inside tanks, water in systems, food in storage, pressure inside walls, shielding around bodies, temperature control, medicine, communication, and machines that must not fail. To live in space is not to live freely. It is to live inside engineering. And that is only the beginning. The moon is close enough to dominate our sky, close enough to brighten the night, close enough to shape tides, close enough to feel familiar. Yet reaching it required one of the most difficult technological efforts in human history. Mars is a neighboring planet, but it is months away by current travel methods, with launch windows, communication delays, radiation exposure, landing risks, and the enormous problem of keeping humans alive far from home. The outer planets are farther still, not just in miles, but in years of mission time, weaker sunlight, colder environments, and longer delays. Robotic spacecraft can go there, Because machines can sleep through distance. They can survive where humans cannot. They can wait years to arrive. They can function without food, breath, psychology, or hope. But even the outer planets are still local. They are still part of our solar system. The nearest stars belong to a different category of distance entirely. This is where intuition fails. Human beings are used to distances that can be crossed. A city can be reached by road. An ocean can be crossed by ship or aircraft. A mountain may be difficult, but it is still on the same human scale. Even the moon, though distant, remains close enough for a round trip within the span of ordinary history. But a star is not far in the way a mountain is far. It is far in a way that breaks the meaning of travel. The nearest star system is several light years away. A light year is not a measure of time, but of distance. The distance light itself travels in 1 year, and light is the fastest thing the universe allows. Even at that ultimate speed, the nearest stars are years away. For human spacecraft moving far slower than light, the journey would not take years. With today's technology, it would take many thousands of years. That is not a trip in the ordinary sense. It is a civilization-scale problem. It is a journey longer than nations, languages, religions, and most institutions survive. It is a journey that turns passengers into descendants, engineering into inheritance, and navigation into an act of deep time. The stars are not unreachable because they are hidden. They are unreachable because they are exposed across distances almost no living body can cross. This is the second paradox. The universe shows us the stars, but not the path to them. Light speed itself becomes part of the trap. The speed of light gives us astronomy. It allows the universe to reach us. It carries the glow of stars, galaxies, nebulae, and the early cosmos into our instruments. Without light, the universe would be invisible. But the same speed that lets us observe distant things also tells us how far away they truly are. The sun is about 8 minutes away by light. That already means we see it not exactly as it is now, but as it was moments ago. The nearest stars are years away by light. Galaxies are millions or billions of years away. The farther we look, the further back in time we see. Astronomy is a kind of time travel, but only in one direction. The universe sends us its past. Traveling there is another matter. A telescope can receive what a body cannot reach. Science can cross distance with information long before life can cross it physically. That may be one of humanity's most important forms of escape. Not escape by movement, but by understanding. We may never touch most stars, but we can know them. We can break their light into spectra. We can measure their motion. We can infer their mass, temperature, composition, age, and fate. We can discover planets around them. We can detect galaxies whose light began traveling before Earth had complex life. Knowledge becomes a way of touching what distance forbids. But knowledge does not erase the trap. It makes it clearer. Space separates not only places, but moments. A message sent to another star would take years to arrive, even if it traveled at light speed. A reply would take years to return. Conversations between star systems would not unfold like speech. They would unfold like archaeology. Civilizations would hear each other across delays longer than human patience, politics, and perhaps even continuity can easily manage. Distance becomes time. Time becomes silence. Silence becomes isolation. This is why the idea of space as a trap is not just about rockets. Rockets are part of it, but they are not the whole story. The trap is built from several layers at once. Distance is the first wall. Light speed is the second. Biology is the third. Gravity is another. Energy, radiation, life support, propulsion, and cosmic expansion add more layers beyond that. No single obstacle explains why the stars are so hard to reach. The difficulty is the combination. The universe is not malicious. It is not designed to imprison us. It has no intention, no will, no architecture built against life. But the laws that allow stars, planets, chemistry, and biology also create limits. They give matter inertia. They make energy costly. They set a speed limit. They stretch distances across cosmic scale. They make living bodies dependent on rare conditions. The same universe that made us possible also made most of itself impossible for us to inhabit. That may be the deepest tension in the night sky. We belong to the universe, but not to all of it. We are made of atoms forged in stars, yet the stars themselves remain beyond any natural human reach. We are cosmic in origin, but planetary in survival. Our minds can imagine interstellar space, but our bodies require a narrow envelope of pressure, temperature, chemistry, gravity, and protection. Consciousness can look outward, but life remains anchored. Space feels like freedom because it has no visible boundary. But freedom without access becomes another kind of confinement. The trap is not that we cannot dream. The trap is that dreaming is easy, while crossing is hard. The stars shine into our eyes, but they do not become nearer. The galaxies reveal themselves to our telescopes, but they do not become destinations. The universe expands around us, filled with countless worlds and possibilities, while physics quietly asks what can actually be reached before time, energy, and biology run out. Earth, then, changes meaning. It is not only the place we begin from, it may be the place that makes beginning possible at all. It is not just a small world under an enormous sky. It is a rare island of safety inside a universe that is mostly not a home. The atmosphere is not a trivial layer. It is the boundary between biology and vacuum. The magnetic field is not a detail. It helps shield the planet from charged particles. Gravity is not only a force holding us down. It holds oceans, air, bodies, and the conditions that make life continuous. To call space a trap is not to call Earth a prison. It is to recognize that Earth may be shelter. The sky above us is not a simple invitation. It is also a warning written in distance. The stars are real. The desire to reach them is real. Exploration is real. But the void between worlds is not a blank road. It is a physical condition with rules, costs, and consequences. The universe looks open, but it is not open in the way our imagination first believes. It is open to light, open to thought, open to mathematics, open to patient machines, open, perhaps, to forms of exploration far slower and stranger than the stories we tell. But for living bodies like ours, space is a trap made of scale, a trap made of time, a trap made of speed limits, fragile biology, and distances so large that even hope must become disciplined. And yet, the trap is not hopeless. It is humbling. It teaches us that the stars are not less beautiful because they are unreachable. They may be more profound because they are unreachable. Their distance forces us to understand before we can possess. It turns astronomy into an act of listening across the impossible. It turns Earth into something more precious than a launch pad. It turns knowledge into a form of travel. We may live on a small island of matter beneath an ocean of dark distance. But from this island, the universe still reaches us. And perhaps the first step toward understanding space is not to imagine it as empty freedom, but to see it clearly for what it is, a vast structure of isolation filled with light from places our bodies may never go. Distance is the first wall, not a wall made of stone, metal, or force, not something you can see rising in front of a spacecraft. Space has no locked gate at the edge of the atmosphere. It does not place a barrier between us and the stars in any ordinary sense. It does something quieter and more absolute. It separates everything by scales the human mind was never built to understand. On Earth, distance has meaning because it can usually be crossed. A person can walk across a room, drive across a country, fly across an ocean. Even the largest distances on our planet remain connected to human time. They are hard, but they are familiar. We can imagine them because our bodies, our maps, and our histories were formed inside them. Space begins by breaking that familiarity. The Moon is the nearest large world beyond Earth, the object that has followed human imagination since before science had language for it. It looks close because it is bright, because it changes shape in the sky, because it belongs to our nights with a kind of intimacy. It is the one celestial body that feels almost reachable to the naked eye. But the Moon is not close in any ordinary human sense. To reach it requires leaving Earth's atmosphere, escaping most of the planet's immediate gravitational hold, crossing hundreds of thousands of kilometers of vacuum, navigating with extreme precision, carrying life support, shielding, fuel, guidance systems, communications, and enough reliability that one failure does not become a death sentence. The Moon is close compared with the stars, but close in space is already dangerous. That is the first lesson. Nearby space is not nearby in the way our instincts understand. The distance from Earth to the Moon is large enough to fit every planet of the solar system between them if they were lined up carefully. That fact feels almost absurd because the Moon appears so familiar. Yet between Earth and its companion, there is enough emptiness to remind us that space begins with separation, even at the smallest cosmic scales. The Moon is our neighbor, and reaching it was still one of the most difficult achievements in human history. Mars seems like the next step. It is often described as a nearby planet, a possible future destination, a world close enough to imagine human footprints in red dust. But Mars is not waiting just beyond the Moon. It moves around the Sun on its own orbit, while Earth moves on another. The distance between them changes constantly. There are times when Mars is comparatively close, and times when it is far across the solar system. Travel to Mars is not simply a matter of pointing a spacecraft and going. It depends on timing. Launch windows matter because planets move. A spacecraft must be sent along a trajectory that meets Mars where it will be, not where it appears at the moment of departure. The journey takes months with current technology. During that time, astronauts would live inside a machine surrounded by vacuum, radiation, and distance. They would not be able to step outside into safety. They would not be able to return quickly. Every system would matter. Every kilogram would matter. Every delay would matter. Even communication becomes part of the distance. A radio message cannot arrive instantly. It travels at the speed of light, which is fast beyond human experience, but not infinite. Depending on where Earth and Mars are in their orbits, a signal can take several minutes to more than 20 minutes one way. That means no real-time conversation in the ordinary sense, no immediate rescue from Earth, no instant command, no instant reassurance, no instant correction. Mars is not only far away in distance, it is far away in response, and that changes the psychology of exploration. On Earth, distance can still feel connected if voices cross it instantly. A person on one continent can speak to another almost in real time. But across interplanetary space, even communication begins to stretch. Presence becomes delayed. Help becomes theoretical. The separation is no longer just measured in kilometers. It is measured in silence between messages. Beyond Mars, the solar system opens wider. The asteroid belt, Jupiter, Saturn, Uranus, Neptune. Each step outward stretches scale further from human intuition. Missions to the outer planets are usually journeys of years. Spacecraft must carry power systems, scientific instruments, navigation plans, and resilience through environments where sunlight becomes weaker and weaker. Solar panels become less effective far from the sun. Temperatures drop. Communication delays lengthen. A signal sent from the outer planets may take hours to reach Earth. The sun itself changes with distance. Near Earth, sunlight feels abundant. It warms the ground, drives weather, powers ecosystems, and defines the rhythm of day. But farther out, the sun becomes a smaller, weaker source of energy. At Jupiter, sunlight is far dimmer than it is near Earth. At Saturn, weaker still. By the time we reach the realm of Uranus and Neptune, the sun no longer feels like the commanding presence it is in our sky. It becomes a bright star among darkness, still dominant by gravity, but emotionally distant. And yet all of this is still the solar system, still home territory in a cosmic sense, still the neighborhood of one star. This is where the scale becomes almost cruel, because after Neptune, after the distant icy bodies, after the outer darkness of our own system, the next star is not simply a little farther away. It belongs to a different category of distance. The space between planets is enormous, but the space between stars is so much larger that ordinary comparison begins to fail. The nearest star system is over 4 light-years away. A light-year is often misunderstood because the word contains year. It sounds like a measure of time, but it is a measure of distance. It is the distance light travels in 1 year. Light moves faster than anything else known in the universe. It crosses the distance from the moon to Earth in a little over a second. It crosses the distance from the sun to Earth in about 8 minutes. But to cross the distance to the nearest star system, light itself needs more than 4 years. That is the scale of interstellar space, not the speed of a rocket, not the speed of a spacecraft, the speed of light. The fastest messenger in the universe takes years to reach the nearest star. For human spacecraft, the difference is devastating. Our fastest probes move at tiny fractions of light speed. At those speeds, reaching the nearest stars would take many thousands of years. The journey would outlast individual human lives by so much that the idea of travel begins to change meaning. It is no longer exploration as we usually imagine it. It becomes a project against time itself. This is why the stars are so misleading to the eye. They appear scattered across the sky like points on a ceiling. They form patterns our minds connect into constellations. They seem arranged across a surface, as though they are all part of the same distant dome. But that is only how the sky presents them. In reality, the stars are at different depths, different distances, different positions in a 3-dimensional galaxy of staggering scale. The sky compresses the universe into beauty. Space expands it back into isolation. A star can look close to another star from Earth, yet they may be separated by vast distances in space. A constellation can look like a group, but its stars may have little physical relationship to one another. The pattern is often ours, not theirs. It is a projection from a planet, a human geometry imposed on depths too large to perceive directly. This is one reason distance is the first trap. It hides behind appearance. The stars do not look unreachable. They shine. They twinkle. They arrive in our eyes. Their light makes them feel present. A photon from a distant star can cross the emptiness and strike a retina, becoming part of human experience. In that moment, the star feels connected to us. It has sent something here. It has entered the mind. But the star itself remains almost impossibly far away. Light makes the universe visible, but visibility is not access. This distinction matters deeply. We often mistake awareness for closeness. We can name a star, measure it, classify it, study its spectrum, infer its temperature, mass, and chemical composition. We can discover planets around it by watching tiny changes in light. We can know extraordinary things about worlds we may never touch. Science allows information to cross distances that bodies cannot. But knowledge travels more easily than life. A signal can cross the void. A spacecraft must survive it. A telescope can receive light. A civilization must spend energy, time, and risk to move matter. And matter is difficult to move across cosmic scale. Every object has mass. Every acceleration requires energy. Every spacecraft must be launched, guided, protected, and slowed if it is meant to arrive rather than simply pass through. The larger the mission, the more severe the problem becomes. A human ship would need habitat, shielding, food systems, medical capacity, repair systems, and enough reliability to outlast the journey. The distance is not just empty length. It becomes multiplied by every requirement survival adds. That is why interstellar space is not merely far. It is hostile through distance itself. Between stars, there are no repair stations, no breathable worlds, no easy refueling stops, no natural shelter, no quick rescue. There is mostly emptiness, dust, radiation, darkness, and time. Even rare material in interstellar space becomes dangerous at high speed. Even tiny particles can carry destructive energy when the spacecraft is moving fast enough. Distance turns small hazards into major concerns because the journey is so long and the margin for failure so thin. The solar system already humbles us. Interstellar space changes the category of the problem. It is the difference between crossing a sea and crossing an ocean of nothing so large that generations could rise and vanish before arrival. It is the difference between exploring a frontier and challenging the structure of the universe. The nearest stars are neighbors only by astronomical standards. By human standards, they are almost unreachable. And yet, they are real. That is what gives the trap its emotional force. The stars are not fantasy. They are not symbolic lights painted on darkness. They are suns, many with worlds, some perhaps with moons, atmospheres, oceans, or conditions we have not imagined. They exist. They burn. They form systems. They may contain places of extraordinary beauty and scientific importance. The tragedy is not that they are imaginary. The tragedy is that they are real and still beyond us. Distance does not deny existence. It denies access. This changes how we think about Earth. When we say Earth is small, we are usually comparing it with the universe. And physically, that is true. Earth is tiny against the scale of galaxies. But from the perspective of life, Earth is immense in meaning. It is a place where distance remains survivable, where air fills the gap between people, where oceans can be crossed, where light and sound arrive quickly, where help can reach, where biology belongs. Space strips away that intimacy. It stretches everything until connection becomes difficult. The moon is close and still hard. Mars is nearby and still dangerous. The outer planets are part of our system and still remote. The nearest stars are close only to the galaxy, not to us. Beyond them, the Milky Way holds hundreds of billions of stars, and beyond the Milky Way are other galaxies separated by distances so large that even light becomes ancient by the time it arrives. The first trap of space is distance so large that human intuition collapses. We can write the numbers. We can define the units. We can say kilometers, astronomical units, light years, parsecs. But the deeper truth is not in the labels. It is in the failure of imagination. The mind tries to shrink the universe into something it can hold, but space refuses to become small. That refusal is not cruelty. It is reality. The stars look close because their light reaches us. The physical space between them is almost unimaginably empty. And in that emptiness, The first wall of the cosmic trap stands silently, not blocking the view, only making the journey almost impossible. Light is the fastest messenger the universe allows. It crosses space with a speed so extreme that, in daily life, it feels instant. Turn on a lamp, and the room seems to fill at once. Look at the moon, and it appears present. Feel sunlight on your skin, and the warmth feels immediate. Our senses are not built to notice the delay, because on human scales, light is almost too fast to matter. But the universe is not built on human scales. Across space, even light begins to feel slow. That is where the trap deepens. Distance does not only separate objects, it separates moments. It turns travel into waiting, communication into delay, and exploration into a confrontation with time itself. The speed of light makes the universe visible, but it also reveals how unreachable much of that universe truly is. The moon is close enough to be our companion in the sky. Its surface can be seen through small telescopes. Its phases shape the night. It feels familiar in a way no other world does. Yet light from the moon still takes a little over 1 second to reach Earth. That delay is small, almost invisible to ordinary perception, but it is real. When you look at the moon, you do not see it at the exact instant of looking. You see it as it was just over a second ago. For the moon, the difference hardly changes anything. But the principle is enormous. The sun is much farther away. Its light takes about 8 minutes to reach us. Every sunrise is already 8 minutes old by the time it arrives. The warmth of daylight, the brightness of noon, the face of the sun in the sky, all of it is a message from the recent past. If the sun could somehow change instantly, Earth would not know at once. The information would arrive only when light had crossed the distance. This does not make the sun less real. It makes reality less immediate. Everything we know about the distant universe arrives late. The farther we look, the further back in time we see. The light from nearby stars can take years to reach Earth. The light from distant galaxies can take millions or billions of years. A telescope is not just a device for seeing far away. It is a time machine in the only way nature truly allows. It receives old light, ancient light, light that began traveling before human civilization, before life on land, before Earth itself in the case of the most distant cosmic signals. This is beautiful. It is also isolating, because the same rule that lets us see the past also limits how quickly anything can be reached, answered, or known. Light speed is not just a number. It is the boundary between what can influence what and when. It is the universe's speed limit for information, causality, and communication. Nothing with mass, according to known physics, can be accelerated to the speed of light. Objects like spacecraft, planets, and human bodies can move fast, but not at light speed. The closer something with mass approaches that limit, the more energy it requires. The speed of light is not merely a technological challenge. It is built into the structure of relativity. This is one reason the stars remain so difficult. Even if a star is only a few light years away, that means light itself needs years to cross the gap. A spacecraft cannot simply match that speed with better engines and ambition. Our current spacecraft move far below light speed. They are fast by human standards, fast enough to leave Earth, cross the solar system, and reach other planets. But compared with light, they are slow, painfully slow. With today's technology, a journey to the nearest star would take many thousands of years. Not years like a long mission, not decades like a heroic exploration. Thousands of years. Long enough for languages to change beyond recognition. Long enough for nations to rise and vanish. Long enough for every living crew member to be replaced by descendants if humans were aboard at all. At that scale, travel stops feeling like travel. It becomes an inheritance problem. A spacecraft bound for another star would not simply carry passengers. It would carry time. It would carry maintenance across centuries. It would carry biological risk, social structure, memory, purpose, and the problem of keeping a mission meaningful to people who never chose to begin it. The distance would not only be outside the ship, it would be inside the lives of everyone connected to it. This is why light speed creates a prison of time. The universe may be filled with stars, but the fastest possible messenger still needs years to move between the nearest ones. Human craft need far longer. Human lives are brief. Human civilizations are unstable. Our technologies age. Our institutions change. Our attention shifts. Space does not need to destroy us to trap us. It only needs to be larger than our timelines. Communication faces the same barrier. Imagine sending a message to a nearby star system. If it is 4 light-years away, the message takes 4 years to arrive, assuming it travels at the speed of light. A reply takes 4 more years to return. One exchange becomes an 8-year cycle. A conversation becomes a monument to patience. And that is the nearest case. Across tens or hundreds of light years, communication begins to resemble archaeology. A question may be sent by one generation and answered by another. Across thousands of light years, civilizations would not talk in any ordinary sense. They would leave signals for distant futures. Across galaxies, the delay grows so enormous that messages become historical artifacts before they arrive. Time becomes distance with a human cost. This matters for any dream of contact. When people imagine civilizations among the stars, they often imagine communication as if distance were a technical inconvenience. Send the signal. Wait for the reply. Build the network. But relativity gives the universe a deeper silence. Even if intelligent life exists elsewhere, even if it transmits, even if it wants to answer, the speed of light turns conversation into something slow, fragmented, and separated from the living moment. A signal can cross the void. A shared present cannot. That may be one of the loneliest facts in cosmology. The universe allows us to see stars as they were, but not necessarily to meet them as they are. It allows us to receive ancient light, but not to step easily into the world that produced it. It gives us a sky filled with information, yet denies us immediate access to the sources of that information. The speed of light is generous to astronomy. It is harsh to travel. Without light, the universe would be invisible. We would not know the stars, galaxies, nebulae, planets, or cosmic background existed beyond our small world. Light carries the fingerprints of distant matter. It tells us what stars are made of. It reveals the motion of galaxies. It shows the presence of planets around other suns. It lets us measure cosmic expansion, map the large-scale universe, and reconstruct histories older than Earth. Light makes the cosmos readable, but readable is not reachable. That distinction sits at the center of the trap. A photon can arrive after crossing unimaginable distance, and we can study it with instruments. But sending a body back along that path is another matter. A human, a spacecraft, a habitat, a supply system, a shielded vessel. These are not photons. They have mass. They need energy. They can break. They can be damaged. They must endure time. The universe lets information travel more easily than life. And even information is limited. No signal can warn faster than light. No command can arrive sooner. No rescue can be coordinated instantly across interstellar space. A spacecraft traveling far from Earth would increasingly leave the realm of immediate human oversight. Instructions would arrive late. Status reports would return late. If something went wrong, the news itself would be old by the time anyone received it. This delay changes the meaning of control. On Earth, we are used to feedback. We press a button and see a response. We speak and hear an answer. We monitor, adjust, repair, command, and correct. Across space, feedback stretches. The farther a mission goes, the more autonomous it must become. The spacecraft must make decisions before Earth knows what happened. Distance becomes not only a physical separation, but a separation of agency. The machine must act alone. The people who built it must wait. The same is true on a larger scale for civilizations. If two worlds are separated by light years, they cannot share events in real time. A disaster, a discovery, a celebration, a warning. All of it travels slowly. By the time one world hears another, the moment has already passed. The present is local. The universe does not share a single practical now across cosmic distance. Relativity teaches this with quiet precision. Time and space are not separate containers. They are woven together. Motion changes how time is measured. Gravity affects the passage of time. Events that seem simultaneous in one frame of reference may not be simultaneous in another. These ideas are not science fiction. They are part of the tested structure of modern physics. But they do not give us an easy escape from distance. Faster-than-light travel remains speculative and unsupported by known physics. Concepts like warp drives, wormholes, and other shortcuts appear in theoretical discussions and fiction, but no demonstrated method allows humans to cross interstellar distances faster than light. Many such ideas require conditions, energies, or forms of matter that may not exist or may not be physically achievable. They remain possibilities on the edge of imagination, not tools we can rely on. That distinction is important. The universe is strange, but strangeness is not permission to ignore physics. Hope does not cancel a speed limit. The speed of light is not merely a challenge waiting for better engineering. It is part of the deep order of reality as we currently understand it. To dream of crossing the stars is human. To understand why that dream is hard is science. Both matter. But only one tells us what the universe has actually allowed so far. This is why time becomes part of the trap. Distance alone would be enough to humble us. But distance multiplied by light, speed becomes a deeper kind of barrier. It means there are places we can see but cannot reach within any meaningful human timescale. It means there may be civilizations we could detect but never converse with normally. It means much of the universe exists for us as light, not as destination. And yet, this limitation is also what gives astronomy its emotional power. Every photon from a distant star is a survivor. It has crossed darkness, passed through dust and emptiness, ignored our impatience, and arrived with information from another place and another time. When we catch it, we are not conquering distance. We are receiving a gift from it. We are learning from something that traveled alone long before we were aware of it. That is a different kind of contact. Not physical arrival, not possession, not settlement. Contact through light, through evidence, through patience. The stars may be unreachable to our bodies, but not entirely unreachable to our minds. We can understand their fusion, their lifetimes, their planets, their motion, their deaths. We can learn how galaxies form, how elements are made, how the universe expands. We can know more than our ancestors could have imagined, even while remaining confined to one world. The trap is real, but knowledge is the crack in it. The speed of light makes the universe readable, but not easily reachable. It lets the stars speak, but slowly. It lets galaxies reveal themselves, but as ancient messages. It gives us astronomy, and at the same time reminds us that seeing a thing does not place it within reach. Space does not only separate objects by distance, it separates lives, civilizations, questions and answers, moments that can never share the same present. And in that separation, the stars become something more complicated than destinations. They become records of a universe that allows us to look outward, but asks us to accept the cost of time. The sky is full of light, but every light has traveled through a prison we cannot easily cross. The universe is not hostile in the way a predator is hostile. It does not hate us. It does not aim at us. It does not try to keep us out. Space is not dangerous because it has intention. It is dangerous because it is almost completely missing everything the human body expects from reality. No air, no pressure, no warmth held in the right balance, no water unless we bring it, no food unless we carry it or grow it inside a machine, no natural shield thick enough to block radiation, no ground beneath the feet, no gravity pulling blood, muscle, bone, and balance into the patterns they evolved to trust. The human body was not built for the void. It was built for Earth. Every cell in us carries that history. We are not just living things placed on a planet by accident. We are shaped by its conditions. Our lungs assume an atmosphere. Our blood assumes pressure. Our bones assume gravity. Our skin assumes a narrow range of temperature. Our eyes assume light filtered by air. Our immune systems, muscles, nerves, organs, and minds all evolved inside a protective envelope that space immediately removes. That is why space becomes a trap at the scale of biology. Distance makes the stars hard to reach. Light speed turns travel into a prison of time. But even before we think about reaching another star, the human body meets a more immediate truth. It cannot survive open space on its own. Not for long. In space, survival is not natural. It is engineered. A spacecraft is not simply transportation. It is an artificial world. It must carry pressure, oxygen, carbon dioxide removal, temperature control, water recycling, food storage, waste management, medical supplies, radiation shielding, communication systems, power, fire, safety, and countless backup systems. It must do what Earth does freely, constantly, and without asking for maintenance. On Earth, life support is not called life support. It is just the world. The atmosphere presses on the body with the right weight. Oxygen enters the lungs. Carbon dioxide leaves. Water cycles through clouds, rivers, soil, and cells. Food grows from ecosystems powered by sunlight. Gravity gives the body orientation. The magnetic field and atmosphere help reduce radiation exposure from space. Temperature varies, but within a range, life can manage across much of the planet. In space, none of this is given. Every breath becomes a system. Every drink becomes logistics. Every safe temperature becomes engineering. Every day alive becomes proof that machines are still working. This is why the dream of space travel must always confront the reality of biology. Rockets may cross distance. Engines may change velocity. Computers may navigate. But inside the vehicle is a body that still belongs to a planet. A body that needs pressure around it. A body that degrades when gravity disappears. A body that can be damaged by invisible particles moving through tissue. A body that is not only a passenger, but the most fragile system on board. Microgravity is one of the clearest examples. When astronauts float, it looks graceful. It looks almost like freedom from one of Earth's oldest limits. A human body drifts through the cabin. Objects hover. Movement becomes light and strange. But microgravity is not a vacation from physics. It is a removal of the load the body evolved to resist. Bones need stress to maintain strength. Muscles need resistance to remain powerful. On Earth, simply standing, walking, lifting, and moving against gravity help keep the body's structure alive. In microgravity, those constant demands weaken. Muscles can shrink. Bones can lose density. The body begins to adapt to an environment where weight no longer behaves normally. That adaptation is useful for floating. It is not necessarily good for returning to a planet. The body also redistributes fluids. On Earth, gravity pulls blood and other fluids downward. In orbit, without the same downward pull, fluids shift toward the upper body and head. Faces can appear puffy. Pressure changes can affect the eyes. The cardiovascular system changes because the heart no longer works against gravity in the same familiar way. Balance systems in the inner ear, trained for a lifetime under Earth's pull, suddenly receive signals that do not match ordinary experience. The body becomes confused because the world it was built for has been removed. Exercise helps. Careful medical monitoring helps. Space agencies have learned a great deal about keeping astronauts healthier during missions. But the fact that countermeasures are needed proves the central point. The human body does not simply move into space and remain unchanged. It begins negotiating with an environment that does not match its design. Radiation is another barrier, less visible but deeply serious. On Earth, the atmosphere and magnetic field provide protection. They do not block everything, but they reduce the exposure of living tissue to many energetic particles from the sun and from beyond the solar system. In deep space, that protection weakens or disappears. Astronauts can be exposed to solar particle events and galactic cosmic rays, high-energy particles that can pass through matter and damage cells. Radiation risk is not dramatic in the way fiction often imagines. It may not announce itself instantly. It can be cumulative. It can increase the chance of cancer. It can affect the nervous system, cardiovascular health, and other biological processes in ways researchers are still working to understand fully. Shielding helps, but shielding adds mass. Mass makes spacecraft harder to launch and accelerate. Every layer of protection becomes part of the engineering burden. This is the pattern again and again. The body needs something. The spacecraft must provide it. Providing it adds mass, complexity, energy demand, failure points, and cost. Food is not simple either. For short missions, supplies can be carried. For long missions, especially deep space or interstellar concepts, the problem changes. A crew would need reliable nutrition for months, years, or longer. Food must be stored, protected, prepared, and managed. If grown on board, plants require light, water, nutrients, space, temperature control, and a stable ecosystem. Waste must be recycled, water must be recovered, air must be cleaned. Biological systems must be kept alive alongside human systems. A closed ecosystem sounds elegant in theory. In practice, it is one of the hardest things humans could attempt. Earth's biosphere is enormous, redundant, self-repairing in many ways, and built by billions of years of evolution. A spacecraft ecosystem would be small, artificial, fragile, and dependent on constant maintenance. It would need to balance chemistry, biology, machinery, human behavior, and time. A mistake would not simply mean discomfort. It could mean the slow collapse of the artificial world keeping the crew alive. Then there is isolation. Space does not only affect tissue, it affects the mind. A human being is not just a body needing oxygen and calories. A person needs contact, rhythm, meaning, privacy, trust, and psychological stability. Long missions mean confinement inside a small environment, repeated routines, limited escape, delayed communication, and a growing awareness of distance from Earth. The planet may remain visible at first, then become a bright point, then perhaps disappear into the larger background. That kind of separation is not ordinary loneliness. It is existential distance. The crew cannot step outside into a park. They cannot go home for a weekend. They cannot breathe unfiltered air, feel rain, walk under trees, or hear the natural disorder of a living world. Their environment is controlled, recycled, monitored, and sealed. Every sound belongs to the machine. Every wall is boundary and protection. Every disagreement happens inside the same closed system that must keep everyone alive. Psychological strain becomes part of the mission architecture. Trust matters, routine matters, sleep matters, communication matters, the sense of purpose matters, the ability to endure boredom, stress, fear, and confinement matters. A spacecraft going far from Earth would not only carry fuel and oxygen, it would carry human emotion under pressure. The farther the journey, the deeper the trap becomes. Near Earth, emergency return may be possible. Around the Moon, the risk grows. On the way to Mars, Earth is no longer an immediate refuge. Across interstellar space, rescue becomes meaningless in any practical sense. The crew would be alone, not because people on Earth did not care, but because physics would make care slow, delayed, and unable to intervene quickly. This is what space does. It turns every human need into an engineering problem. It turns every weakness into mission risk. It turns every distance into delayed help. And it reminds us that exploration is not the same as belonging. The human body belongs to Earth in ways that are difficult to feel while standing safely on it. Gravity is so constant we forget it is supporting our biology. Air is so available we forget our dependence on pressure. Water is so familiar we forget that liquid water exposed to vacuum is not a stable comfort. The sky seems open, but it is also protection. The ground seems ordinary, but it is the surface of the only environment where human life can exist without machinery wrapped around it. To leave Earth is not simply to travel. It is to remove the body from its native operating system. This does not mean humans should never explore space. It does not make exploration pointless. The ability to send people beyond Earth is extraordinary, and the knowledge gained from human and robotic missions matters deeply. But romance must not erase biology. Space is not a natural human environment waiting to be settled like a new continent. Continents had air. Oceans had water. Deserts still had gravity and pressure. Even the harshest places on Earth remain part of the biosphere. Space is different. It is not empty land. It is absence. And that absence is total enough that survival must be continuously manufactured. This is why the idea of living among the stars is so difficult. Not only because the stars are far away, but because between them there is no natural continuity with life. There is no breathable path, no ecological corridor, no chain of safe islands waiting at convenient intervals. There is mostly vacuum, radiation, cold darkness, rare particles, and distance. If humans ever travel far beyond the solar system, they will not be conquering the void by becoming independent from Earth. They will be carrying Earth in miniature. A ship would need to become a moving fragment of the planet, sealed, powered, shielded, and maintained across time. It would be less like a vehicle and more like an artificial biosphere, a fragile island of pressure and warmth moving through an environment that offers none of those things. That is the biological truth behind the cosmic trap. Space is not only far, it is incompatible. It does not meet the body halfway. It does not provide the basics and ask us to solve the rest. It provides almost nothing and then punishes failure quickly. The body must be protected from vacuum, radiation, microgravity, isolation, starvation, dehydration, overheating, freezing, infection, injury, and system breakdown. Every solution creates new requirements. Every requirement deepens the dependency on technology. And underneath all of it is a simple fact. Life evolved for Earth, not for the void. Our bones, blood, Lungs, skin, senses, and minds are records of that origin. We are planetary beings with cosmic curiosity. We can imagine the stars, study them, name them, dream of reaching them. But our biology remains tied to one rare environment where matter, gravity, chemistry, and temperature came together in the right way. The universe is vast enough to inspire us, but it is not made for us. That is not a reason for despair. It is a reason for humility. It tells us that Earth is not merely a starting point to be left behind. It is the condition that made every thought of leaving possible. The atmosphere, the oceans, the gravity, the magnetic shielding, the biosphere. These are not background details. They are the cradle of the only bodies we have. Space is a trap because the human body is not a creature of emptiness. It is a creature of air, water, pressure, gravity, and living systems. And beyond Earth, every one of those must be carried, rebuilt, or protected by machines that can never be allowed to fail. Every journey into space begins with a contradiction. Earth is the thing we dream of leaving, and Earth is the thing that makes leaving so difficult. It gives us air, oceans, warmth, pressure, chemistry, and shelter. It holds the atmosphere close. It keeps our bodies anchored. It gathers water into seas, pulls rain back toward the ground, and gives life a stable surface on which to evolve. Without Earth's gravity, there would be no world like the one we know. No oceans resting in basins. No breathable sky wrapped around the planet. No bodies walking, falling, sleeping, or growing in the way they do. Gravity makes Earth a sanctuary. But the same force that holds the sanctuary together also makes it hard to escape. A planet is not just a place. It is a gravitational well. To leave it, you do not simply go upward. You must climb out of a deep, invisible valley made by mass. The surface of Earth is at the bottom of that valley. Orbit is not freedom from it. The moon is not beyond it entirely. Even far from the planet, Earth's pull does not vanish suddenly. It fades with distance, but it keeps shaping motion long after the ground has disappeared below. This is why space travel begins before space. It begins with fighting the planet that made us. A rocket on a launch pad is often described as a vehicle. But in a deeper sense, it is an answer to gravity. It must lift itself, its engines, its structure, its payload, its computers, its life support systems if humans are aboard, and above all, its fuel. Then it must lift the fuel required to lift that fuel. And then more fuel is needed to lift the added fuel, and structure must be strong enough to contain it, and engines must be powerful enough to accelerate it. The problem folds back on itself. Every kilogram matters. A camera matters. A tool matters. A seat matters. A tank wall matters. A bolt matters. A person matters. A spare part matters. A kilogram of food matters. A kilogram of shielding matters. Add mass, and the rocket needs more energy to move it. Add more fuel to provide that energy, and now the rocket is heavier. That extra weight demands still more fuel. The logic is relentless. This is the heart of the rocket problem. Not in symbols, but in consequence. A rocket must spend most of itself simply to become fast enough and high enough to remain in space. Much of its mass at launch is propellant. The towering machine that rises from Earth is not mostly cabin, payload, or destination. It is stored chemical energy, structure, engines, guidance, and the temporary violence required to climb out of a gravitational well. Launch is not gentle because gravity is not negotiable. The rocket must accelerate while gravity pulls it downward. It must push through the lower atmosphere, where air resists it and pressure loads strain the vehicle. It must survive vibration, heat, acoustic shock, engine stress, and the constant narrowing of margins. The path to orbit is not simply a climb. It is a carefully controlled escape through layers of physics that punish weakness. And reaching orbit does not mean stopping. This is one of the great misunderstandings of space. Orbit is not a place where gravity is gone. Astronauts float not because Earth has stopped pulling them, but because they are falling around Earth continuously. Their spacecraft moves forward so fast that as it falls, the planet curves away beneath it. Orbit is a state of motion, not a cancellation of gravity. To stay in orbit, you must move sideways at tremendous speed. To leave orbit, you must change that motion. To reach another world, you must match the geometry of moving bodies around the sun. There is no simple straight road. This is why, even after leaving the ground, travelers are not free. They are still bound by orbital mechanics. Every destination is moving. Earth moves. Mars moves. The moon moves. Asteroids move. Spacecraft follow curves shaped by gravity and momentum. A mission must be timed, aimed, corrected, and paid for in velocity. Not velocity as a simple measure of speed, but as the ability to change motion. In space, changing motion is currency, and the currency is limited. Fuel becomes time. Fuel becomes options. Fuel becomes survival. Once a spacecraft has used its propellant, it cannot simply decide to go somewhere else. It cannot stop on command without energy. It cannot turn a wrong path into a right one unless enough capacity remains. The emptiness of space may look open, but trajectories are disciplined by mathematics. A small mistake can grow across distance. A missed timing window can delay a mission for years. A destination may be near in imagination, but inaccessible until the geometry permits it. This is especially clear with Mars. Earth and Mars both orbit the Sun, but they do not remain at a constant distance. To travel efficiently, spacecraft are usually launched during windows when the planets are positioned favorably. Miss that window, and the next practical opportunity may not come soon. The planets do not wait for human schedules. They move according to gravity, and missions must adapt to them. Space is not empty freedom. It is moving architecture. Every voyage is negotiated with gravity. The same is true when arriving at another world. Reaching a planet is only half the problem. You must slow down. If the planet has an atmosphere, that atmosphere can help brake the spacecraft, but it also creates heat, pressure, turbulence, and danger. If the world has little or no atmosphere, you may need engines to slow the descent. Landing requires precision. Too much speed, and the mission ends violently. Too little control, and the spacecraft misses the target, tips over, crashes, burns, or disappears. A planet's gravity pulls you in. Then it demands payment if you want to leave again. Landing on the moon is difficult, but leaving the moon is easier than leaving Earth because the moon has weaker gravity and no thick atmosphere. Mars is more complicated. It has lower gravity than Earth, but enough atmosphere to create entry challenges and not enough atmosphere to make landing easy. A human mission to Mars would need to land heavy equipment, support the crew, and eventually launch them back into space. That return launch means engines, fuel, structure, and reliability waiting on another planet. The trap follows us. Escape from Earth is expensive. Escape from Mars would also be expensive. Escape from any significant world carries a cost written by gravity. This is why some visions of future space exploration look toward moons, asteroids, orbital stations, or fuel made from local resources. If propellant can be produced away from Earth, or if construction can happen in lower gravity environments, then some of the burden may be reduced. But those are not simple solutions. They require infrastructure, mining, processing, power, storage, machines, human or robotic labor, and time. They move the difficulty rather than erase it. There is no free path outward. Every solution creates another system that must exist first. This is the energy debt of space travel. To go anywhere, matter must be moved. To move matter, energy must be spent. To spend energy, fuel or power must be available. To carry fuel, mass increases. To handle mass, structures grow. To support structures, more energy is needed. The loop shapes every mission from the smallest probe to the largest imagined starship. A spacecraft is never just a dream with engines attached. It is a negotiation with mass. This is one reason interstellar travel is so hard. It is not only the distance between stars that overwhelms us. It is the energy required to send matter across that distance at meaningful speed. A slow probe could take tens of thousands of years. A faster craft would require far more energy, more shielding, more precision, and some way to slow down at the destination if it is meant to study or settle rather than simply fly past. The faster the dream, the larger the debt. The universe does not forbid motion. It charges for it. On Earth, movement is made easy by infrastructure. Roads, ships, aircraft, fuel stations, airports, ports, maintenance networks, rescue systems, and global communication make travel feel normal. We forget that mobility is not only about vehicles, it is about everything that supports them. In space, almost none of that exists naturally. The first travelers must bring the road, the shelter, the power, the repair shop, the navigation system, and the emergency plan with them. And before they bring any of it, they must lift it out of a gravity well. This gives Earth a strange double meaning. It is the cradle of life, but also the first barrier to the cosmos. Its gravity protects and imprisons. Its atmosphere shelters and resists launch. Its mass gives us oceans, weather, and biological stability, while demanding tremendous energy from anyone who wants to leave. The same planet that makes life possible makes escape costly. That is not a flaw in Earth. It is the condition of being a world. A small asteroid would be easier to leave, but it would not naturally provide oceans or air. A massive planet can hold an atmosphere, but escape becomes harder. A habitable world must have enough gravity to keep the ingredients of life close, and that same gravity becomes the price of departure. Life may arise most comfortably in places that are difficult to leave. There is a quiet irony in that. The better a world is at holding life, the harder it may be for that life to step away from it. This is why the trap begins long before interstellar space. It begins under our feet. It begins with the force that gives us weight. It begins with the cost of climbing from the bottom of a planetary well into a sky that is not truly a destination, but the first layer of a much larger problem. Even orbit is not release. It is only a new kind of dependence. A spacecraft in orbit must manage drag if low enough, avoid debris, maintain power, control temperature, preserve orientation, and sometimes adjust its path. A vehicle heading beyond Earth must perform precise burns, conserve fuel, handle communication delay, and obey the timing of moving worlds. The farther it goes, the fewer easy corrections remain. Freedom in space is always conditional. The language of exploration often speaks of breaking free. Physics speaks more carefully. You do not break free from gravity all at once. You trade one gravitational relationship for another. Leave Earth, and the Sun dominates. Approach Mars, and Mars takes over. Pass Jupiter, and its enormous mass can bend your path. Spacecraft can even use gravity assists, borrowing motion from planets to change trajectory. Gravity is not only an obstacle, it can be a tool. But even as a tool, it must be respected. The trap is not that gravity always stops us. The trap is that gravity always has to be paid attention to. It shapes the map before the journey begins. And so the dream of the stars must pass through the first account book of the universe: mass, energy, fuel, timing, and motion. Before biology faces radiation, before communication stretches across years, before cosmic expansion removes galaxies from reach, there is the launch pad. There is the weight of the rocket. There is the fuel inside its tanks. There is the planet pulling everything downward. Gravity makes every escape from a world expensive. That expense is not only financial, it is physical, it is energetic, it is structural, it is risk. It is the reason a journey into space begins with fire, thunder, precision, and danger. It is the reason every kilogram must justify itself. It is the reason humans do not simply step into the universe, even though the universe begins just above the air. Earth holds us because Earth made us. To leave it, we must build machines powerful enough to argue with the force that keeps the world intact. And even when those machines succeed, they do not remove the trap. They only carry us deeper into it. The idea of traveling to another star sounds simple only from a distance. Build a faster spacecraft. Point it toward a nearby sun. Leave the solar system behind. Cross the dark. Arrive at a new world. The sentence is easy. The physics is not. Going to the stars is not one problem. It is thousands of problems stacked together, each one touching the others. Speed is only the first. A starship must accelerate, survive, navigate, communicate, protect itself, maintain power, manage heat, resist radiation, avoid dust, preserve information, and perhaps keep human beings alive across durations longer than any ordinary mission has ever approached. Interstellar travel is not blocked by a single wall. It is blocked by a chain. And every link in that chain is made of reality. The first question is propulsion. How do you make a spacecraft move fast enough for the journey to have meaning? Chemical rockets, the machines that lifted humans from Earth and sent probes across the solar system, are extraordinary achievements. But they are not built for the stars. They can escape Earth, cross planetary space, and send machines toward the outer solar system. But compared with the distance between stars, their speed is painfully small. At current spacecraft speeds, a journey to the nearest star would last many thousands of years. That is not exploration as we usually imagine it. It is a message in a bottle thrown across deep time. To shorten the journey, a spacecraft must move much faster. But speed is expensive. The faster you want to go, the more energy you must invest. And if you want to carry a large spacecraft, with instruments or shielding or people, the problem grows. Moving a tiny probe is difficult. Moving a human-scale vessel is far harder. Moving a self-sustaining world across interstellar space becomes almost unimaginable. This is why scientists and engineers have considered more powerful ideas. Nuclear propulsion could, in principle, provide higher performance than chemical rockets. Nuclear thermal concepts use reactor heat to drive propellant. Nuclear electric systems could produce electrical power for efficient engines over long periods. These ideas are not magic, and they do not erase the scale of the stars, but they may offer better paths through the solar system and perhaps help with missions beyond it. Fusion propulsion is even more ambitious. Fusion is the process that powers stars, and a spacecraft able to use it efficiently could, in theory, reach speeds far beyond conventional rockets. But controlled fusion for practical energy remains one of the hardest technological challenges humanity has ever pursued. Turning fusion into a reliable, compact, long-lived propulsion system for deep space would add layers of difficulty beyond the already immense challenge of making fusion work on Earth. Then there are light sails. A light sail uses radiation pressure, the tiny push of light itself, to accelerate a spacecraft. If the craft is extremely small and the sail is driven by powerful lasers, it might be possible to send lightweight probes toward another star at a significant fraction of light speed. Such probes could arrive within a human lifetime, at least in some concepts. But the trade-off is severe. The spacecraft must be small. The sail must survive intense illumination. The laser system must be enormous, precise, and coordinated. The probe must then cross interstellar space, survive the journey, gather data, and send a signal back across years of distance. A light sail may help solve the speed problem for tiny machines. It does not solve the problem of carrying humans. Antimatter is sometimes imagined as the ultimate fuel. Matter and antimatter can release enormous energy when they meet. In principle, this makes antimatter attractive for propulsion. In practice, antimatter is extremely difficult to produce, store, and handle. The amounts needed for serious propulsion would be far beyond anything humans can currently manufacture or contain. It remains an idea at the edge of physics and engineering, powerful in theory, but distant from practical reality. Every propulsion concept reveals the same truth. The stars demand energy at a scale that makes ordinary travel feel primitive. But even if a spacecraft could move fast enough, speed is not survival. A mission to another star must endure time. For a robotic probe, that may mean decades, perhaps longer. For a human vessel, it may mean generations. And time is not passive. Time corrodes systems. Electronics degrade. Materials fatigue. Radiation accumulates. Mechanisms fail. Software errors emerge. Power systems weaken. A spacecraft cannot simply be launched and assumed to remain perfect. It must last. And it must last without a repair shop, without resupply, without emergency rescue, and with communication delays so long that help from Earth would arrive as advice from the past. Navigation becomes another problem. In the solar system, spacecraft can use radio tracking, star trackers, onboard sensors, and gravitational assists. Between stars, the distances are larger and the margins are different. A small error in direction can become enormous over years or decades. The target star is moving. The spacecraft is moving. The sun is moving within the galaxy. Nothing waits. A starship must not only aim at where a star is, it must aim at where the encounter will be. And if the craft is moving very fast, arrival becomes its own challenge. Passing another star at high speed may allow a brief flyby, but slowing down enough to enter orbit or study planets in detail requires more energy, more propellant, or a carefully planned braking method. A mission that can reach the stars but cannot slow down may spend decades crossing the void for a few hours of encounter. Interstellar dust adds a quieter danger. Space between stars is emptier than any vacuum we can make on Earth, but it is not perfectly empty. There are atoms, particles, dust grains, and cosmic rays. At ordinary speeds, dust may seem trivial. At a significant fraction of light speed, even a tiny grain can strike with destructive force. A small particle becomes a high-energy projectile. The faster the spacecraft travels, the more severe the threat becomes. Shielding is possible, but shielding has mass, and mass returns us to propulsion. More shielding means more weight. More weight means more energy to accelerate. More energy means more fuel or a more powerful propulsion system. The solution to one problem becomes a burden on another. This is the rhythm of interstellar engineering. Nothing is isolated. Every answer changes the question. Radiation is similar. Cosmic rays and high-energy particles can damage electronics and biological tissue. A robotic probe needs hardened systems. A human crew needs much more protection. Shielding people is harder than shielding circuits because people are fragile, wet, complex, and irreplaceable. The longer the journey, the more radiation exposure matters. The more shielding added, the heavier the ship becomes. Humans make the problem vastly harder. A human starship is not simply a spacecraft with seats. It is an ecosystem, a society, and a medical facility sealed inside a machine. It must provide air, water, food, gravity, or a substitute for gravity, radiation protection, sanitation, sleep, privacy, exercise, psychological stability, and meaningful work. It must maintain itself for a duration beyond the life of many technologies. It must survive fire, disease, conflict, mechanical failure, resource imbalance, and human error. If the journey lasts longer than a human lifetime, the ship becomes something even stranger, a generation ship. In concept, a generation ship carries a community that lives, dies, and reproduces during the journey. The people who arrive are not the people who left. They are descendants, born inside a vessel moving through darkness toward a destination chosen before their birth. Technically, the idea does not violate known physics. But the practical and ethical challenges are immense. How do you build a closed habitat stable for centuries? How do you maintain machinery across generations? How do you preserve knowledge, purpose, and consent? How do you govern a society that cannot leave its environment? How do you prevent cultural collapse, social conflict, or loss of mission identity? How do you justify choosing a destination for people who may never have known Earth? A generation ship is not only an engineering project, it is a moral experiment. It asks whether human beings can turn a spacecraft into a civilization without turning the mission into a prison. It asks whether survival alone is enough, or whether a life confined to an artificial world can remain psychologically and culturally whole. It asks whether reaching another star is worth the cost paid by those born between the worlds. This is why robotic probes may be more plausible. Machines do not need air, food, gravity, sleep, community, or meaning. They can be small, hardened, patient, and specialized. A probe can cross distance in silence. It can endure cold, darkness, and time more easily than a crew. It can be sent where humans cannot yet go, and perhaps where humans should not go until much more is understood. But even robotic probes face deep challenges. They need power that lasts. Solar energy weakens with distance from the sun, and beyond the solar system it becomes almost useless for many mission types. Radioisotope power systems may last years or decades, but interstellar timelines strain every power source. Electronics must survive radiation and aging. Instruments must remain functional after long dormancy. Navigation must remain precise. Communication back to Earth becomes difficult because signals weaken across distance, and a tiny probe may have little power to transmit. A message from another star would arrive faint and delayed. Receiving it would require patience, sensitive instruments, and faith that something launched decades or centuries earlier still works. Even if a probe succeeds, the data arrives slowly. A flyby of a nearby star system might produce observations, but the return signal would take years to reach Earth after the encounter. Humanity would not watch the discovery in real time. We would receive it later, as light crossing the same distance that trapped the spacecraft. Interstellar exploration, then, may not feel like adventure. It may feel like waiting for ghosts. Launch a machine. Let it vanish. Wait through years of silence. Hope that one day a whisper returns. And yet, this may be the most realistic form of reaching the stars for a long time. Not humans stepping onto alien soil, but instruments crossing the dark ahead of us. Not colonies, but measurements. Not conquest, but contact through data. That may seem disappointing only if exploration is imagined as possession. Science does not always require arrival by body. Sometimes it begins with a signal, a spectrum, a shadow across a star, a tiny shift in light. Humanity has already discovered planets it cannot reach. It has mapped galaxies it cannot visit. It has listened to the universe across wavelengths and distances no body could cross. Machine probes would be another step in that pattern, extending our senses where we cannot yet send ourselves. Still, the dream of human travel remains powerful because it touches something older than science. To go there, to stand under another sun, to see whether Earth is unique not only in data but in experience. That dream is real. But the universe does not bend because a dream is beautiful. It asks for solutions, propulsion, power, shielding, navigation, reliability, communication, habitat, medicine, governance, psychology, ethics, time. Each one is difficult on its own. Together, they form the interstellar problem no rocket can ignore. A rocket can provide thrust, but thrust alone does not create a civilization that can survive the void. An engine can shorten a journey, but it cannot remove radiation, dust, mechanical failure, human fragility, or the silence between stars. This is the deeper nature of the trap. The barrier is not one door we have failed to open. It is a corridor of doors, each locked by a different law of physics, biology, or engineering. Open one and another remains. Solve speed and survival remains. Solve survival and energy remains. Solve energy and communication remains. Solve communication and time remains. Solve the machine and the human question remains. The stars are not unreachable because humanity lacks imagination. They are unreachable because imagination must eventually become hardware, energy, material, biology, and endurance. To say go to another star is to compress centuries of unsolved problems into 5 words. Interstellar space is not empty in the comforting sense. It is empty of support, empty of infrastructure, empty of mercy. A spacecraft crossing it must become its own world, its own power plant, its own shield, its own memory, and perhaps its own society. It must carry the conditions of life across a region that offers almost none. That is why the stars remain so distant, not only because they are far away, but because every attempt to reach them must fight distance with machinery, time with reliability, emptiness with systems, and isolation with purpose. The universe does not place one wall between us and the stars. It places thousands, and each one must be understood before it can be crossed. There is a distance beyond engineering, not because our rockets are too weak, or because our fuel is too limited, or because the human body is fragile in the void. Those barriers are real. They already make the stars difficult enough. But beyond them is a deeper limit, one that does not belong only to spacecraft, biology, or technology. It belongs to the universe itself. For most of human history, the stars seemed fixed. They rose and set with the seasons. They formed patterns across the sky. They felt eternal, distant, but stable. The universe appeared like a vast stage on which planets moved and stars burned in place. Then modern cosmology changed that picture. The universe is not static. Space itself is expanding. This does not mean galaxies are simply flying through empty space like fragments from an explosion. It means the distance between large-scale regions of the universe is increasing because the fabric of space is stretching. Galaxies are not moving away only through space. In a deeper sense, space is growing between them. That difference matters. A rocket can move through space. A signal can cross space. Light can travel through space at the ultimate speed limit. But if space itself is expanding, then the meaning of distance changes over cosmic time. The path between two places is not just a fixed road waiting to be crossed. The road can grow while light is traveling across it. This is where the trap becomes cosmic. Nearby galaxies, especially those bound together by gravity in our local region, do not simply drift apart in the same way as the most distant galaxies. Gravity can hold groups and clusters together against cosmic expansion. The Milky Way, Andromeda, and other nearby galaxies are part of a local gravitational neighborhood. On these scales, gravity still dominates. The expansion of the universe does not pull apart everything everywhere. But far beyond our local region, the story changes. Distant galaxies are carried away as space expands. The farther they are, the faster that recession appears. This is not because every galaxy has engines pushing it away from us. It is because there is more expanding space between us and them. With enough distance, the accumulated expansion becomes enormous. Some galaxies are already so far away that reaching them is not merely difficult. It is impossible in principle. Even if we could build a spacecraft that traveled close to the speed of light, even if it launched immediately, even if it never failed, there are regions of the universe it could never reach. The space between us and those regions is expanding in such a way that the destination would remain forever beyond contact. The craft could move at the greatest speed allowed by physics, and still the cosmic distance would defeat it. This is not a failure of engineering. It is a feature of space-time. The idea can feel almost unfair. The universe contains galaxies, stars, planets, and perhaps countless worlds. They exist. They are not imaginary. Some of their light may still be arriving here. We can study them. We can photograph them. We can measure their redshifts, their masses, their structures, their histories. They can be part of our knowledge, but they cannot be part of our future travel. They are visible and unreachable at the same time. That is one of the most haunting truths in cosmology. There are places whose light can reach us now, but that we could never reach, no matter how advanced our technology becomes under known physics. Their ancient photons are still able to cross the universe and enter our telescopes, but if we tried to send a ship toward them today, the expansion of space would prevent the ship from ever arriving. Seeing is not reaching. Again, the universe makes that distinction sharper. A cosmic horizon is not a wall in space. There is no physical surface where a spacecraft would strike something and stop. There is no edge marked by matter, no barrier of stone or energy. A horizon is a limit in relationship. It is a boundary defined by what can influence, what can be observed, what can be reached, and what can ever exchange signals across cosmic time. Earth has horizons because the surface curves and because light travels through air and space. Cosmology has horizons because light has finite speed and the universe has a history. There has only been a finite amount of time since the hot early universe. Light from very distant regions has not had unlimited time to reach us. And because the universe continues to expand, some light emitted far away may never arrive at all. This means the observable universe is not the whole universe. It is the region from which light has had time to reach us. Beyond that may be more universe, perhaps much more. More galaxies, more stars, more structure, more history. But if their light has not reached us, they remain beyond observation. And if expansion keeps carrying regions apart, some of them may remain forever outside our cosmic contact. The universe contains more than we can see. And even within what we can see, it contains more than we can touch. This is a difficult idea because human intuition treats visibility as a kind of access. On Earth, if something can be seen, it is usually somewhere within the same practical world. A mountain seen on the horizon can be reached by walking, climbing, driving, or flying. A city seen from above is part of the same planet. Even if the journey is hard, it belongs to ordinary possibility. Cosmology breaks that relationship. A galaxy can be seen and unreachable. A star can be real and permanently inaccessible. A region of space can be present in our telescopes but absent from any future path. That is not because it is hidden. It is because space-time itself changes the meaning of reachability. The expansion of the universe turns distance into destiny. Over enormous timescales, the effect becomes even more severe. Distant galaxies that we can observe today may slowly fade from future visibility as expansion carries them farther away and stretches their light. Their signals become weaker, redder, and more delayed. Eventually, for civilizations in the far future, much of the universe beyond the local gravitational neighborhood may disappear from view. The night sky of the distant future could reveal far less of the cosmos than we can see today. There is something fragile about that. We live at a time when the universe is still widely readable. The light of distant galaxies still reaches us. The evidence of cosmic expansion, the background radiation from the early universe, the large-scale structure of galaxies. These clues are still available. Cosmology is possible because the universe has not yet hidden too much of itself from us. But that window is not eternal. The universe is not only expanding through space, it is carrying information into silence. This gives the trap a deeper meaning. Space isolates worlds by distance. Light speed isolates moments by time. Biology isolates life inside fragile conditions. Gravity demands energy from every escape. Engineering turns every mission into a chain of unsolved problems. But cosmic expansion adds something colder. It says that even if all local barriers were overcome, even if we became unimaginably skilled at travel, the universe has boundaries of contact that no ship can cross. There are destinations that do not become reachable with patience. There are destinations that patience makes farther away. This does not mean every star is beyond us. It does not erase the possibility of future exploration within the solar system, or perhaps, one day, nearby stars. It does not mean the Milky Way is instantly inaccessible or that local space is being pulled apart in the everyday sense. Gravity still matters. The galaxy still holds its stars. Nearby systems remain part of the larger question of advanced exploration. But the full universe is not open to us. That is the essential point. The cosmos is larger than any possible empire of movement, larger than any map of destinations, larger than any future migration. Even a civilization with enormous technology would face horizons built not from weakness, but from geometry and time. The trap is not only that humans are small, it is that the universe has a structure in which contact itself has limits. This changes the emotional meaning of the stars. When we look into deep space, we are not looking at a territory waiting to be claimed. We are looking at a history we are lucky enough to receive. The light from a distant galaxy is not a promise that we can go there. It is evidence that the universe once allowed that information to cross the gap. It is a message from a place that may already be beyond all possible reach. In a way, astronomy is the art of receiving what travel cannot deliver. We cannot visit most galaxies, but their light visits us. We cannot step into the early universe, but ancient radiation still fills space. We cannot touch the farthest structures, but we can measure the patterns they leave in light. The cosmos gives us access through information, not possession. That may be the most realistic form of cosmic contact. Not arrival, not conquest, not permanent expansion into every direction, but understanding. The universe may keep many of its places beyond our reach, while still allowing their signals to enter our instruments and minds. That is not nothing. It is one of the strangest gifts of physics. We are trapped locally, but not blind. We are isolated in motion, but not completely isolated in knowledge. Still, the limit remains. Some galaxies are leaving our future. Some regions will never send signals we can receive. Some places whose light we see today could never be reached by anything we send. Space is not simply too big. It is dynamic. It evolves. It carries galaxies apart. It builds horizons into the relationship between observer and object. The trap is not just distance. It is expanding distance. It is not just that the stars are far. It is that some parts of the universe are becoming more unreachable with every passing moment. There is a humility in this that science does not soften. It sharpens it. The more we learn, the less the universe resembles a human-scaled frontier. It is not a stage built around our movement. It is a vast, evolving space-time in which matter, radiation, gravity, expansion, and time create possibilities and limits long before intelligence appears to ask questions. We are late arrivals in an ancient cosmos. We inherit light from places we cannot join. We build theories about regions we cannot affect. We discover that the universe is not only bigger than our bodies, but bigger than our future. And yet, this knowledge does not make the search meaningless. It gives the search a different dignity. To understand what cannot be reached is still a profound act. To know the shape of the horizon is to know something true about reality. To recognize a limit is not failure. It is contact with the deep structure of the world. The trap becomes visible only because consciousness can measure it. A planet-bound species, made of fragile bodies, has learned that space-time expands. It has learned that light carries history. It has learned that some galaxies are beyond future reach. That knowledge does not free us physically, but it changes what captivity means. We are not trapped in ignorance. We can map the walls, even when we cannot cross them. Some stars and galaxies are unreachable not because we are weak, but because the universe itself puts them beyond contact. That is the final scale of the problem, not a technical delay, not a missing engine, not a temporary weakness. A cosmic boundary written into expansion, time, and the finite speed of light. The universe contains more than we can ever touch, more than we can ever visit, more than any civilization could gather into its experience. It is not a treasure house waiting for hands. It is a reality whose depth exceeds access. And perhaps that is why deep space feels both beautiful and severe. Its light reaches us across impossible distance, carrying proof that something is there. But behind that light, the road continues to stretch. And some roads, in an expanding universe, do not lead to arrival. Space is a trap, but not because the universe is cruel. There is no intention behind the distance. No hidden design meant to keep life confined. No cosmic wall built to deny us the stars. The universe does not forbid us from leaving Earth in anger or judgment. It simply exists according to laws that are older than life, older than planets, older than every mind that has ever looked upward and wondered what lies beyond the dark. The trap is not moral. It is physical. It is distance, stretched beyond instinct. It is light speed, turning separation into time. It is biology, reminding us that the human body was shaped by air, pressure, water, gravity, and a narrow range of conditions. It is gravity, making every escape from a world expensive. It is energy, forcing every dream of motion to pay a cost. It is engineering, turning the phrase, "go to the stars," into thousands of unsolved problems. And beyond all of that, it is cosmic expansion, carrying some galaxies away so deeply that no future signal, ship, or civilization could ever reach them. This is what makes space different from every frontier humans have ever crossed. A mountain can be climbed, an ocean can be sailed, a desert can be mapped, a continent can be crossed, slowly and dangerously, but crossed. Space is not like that. It is not a larger version of Earth's wilderness. It is not empty land waiting beyond a border. It is a condition so unlike the world that made us that survival itself becomes artificial. It offers no air by default, no warmth by default, no pressure by default, no food by default, no repair, no rescue, no easy return. And still, it shines. That is the strange power of the night sky. The stars look near enough for imagination. They enter the eye as points of light. They seem quiet, fixed, almost patient. They have been used as maps, symbols, gods, calendars, and questions. They give the impression of presence. A star can be many light years away, yet its light can arrive in a human eye in a single silent instant of perception. But the perception is not the journey. Light reaches us more easily than we can reach the light's source. This is the central wound in the dream of the stars. The universe allows us to see far more than we can touch. It allows us to receive messages from distances that our bodies may never cross. It gives us evidence without access, beauty without possession, knowledge without arrival. The stars are real. But most of them are not destinations in any human sense. That sentence can feel harsh, because so much of our imagination has been built around the idea of outward movement. Human history is full of departures. We left valleys, crossed rivers, built ships, launched aircraft, sent machines to other worlds, walked on the moon, and placed observatories beyond the atmosphere. Exploration is not a fantasy. It is part of what intelligence does when it discovers a boundary. But the stars are not just another boundary. They are a boundary of scale. The nearest stars are far enough that current spacecraft would take thousands of years to reach them. A conversation with another star system, even by light, would unfold over years at best. A human mission would have to carry a fragile piece of Earth across emptiness. A generation ship would raise ethical questions as difficult as its technical ones. A probe might be more realistic, but even a probe would face power limits, radiation, dust, navigation, and the slow fading of signals across distance. The trap is not a single locked door. It is a landscape of limits. Each limit can be studied. Some may be softened. Some may be worked around. Faster propulsion may be developed. Better shielding may be built. Closed life support systems may improve. Robotic explorers may travel farther than humans. New physics may surprise us. But the structure of the problem remains. Space does not become easy because we understand it better. Often, understanding it better reveals why it is harder than we thought. This is not a reason for despair. It is a reason for clarity. To understand the trap is not to surrender to it. It is to stop confusing the universe with the stories we prefer. The real cosmos is not built around human convenience. It is not scaled to our lifetimes, our politics, our desires, or our myths of conquest. It is vast in ways that defeat ownership. It is old in ways that make ambition look brief. It is dynamic in ways that can carry galaxies beyond every future reach. And yet, from one small planet, we have learned this. That may be the most astonishing fact of all. A species bound to a world has measured the depth of its own confinement. We have learned that light takes time. We have learned that stars are suns. We have learned that galaxies recede as space expands. We have detected planets around distant stars. We have seen the afterglow of the early universe. We have sent machines beyond the planets. We have built equations, instruments, and ideas powerful enough to reveal limits that no body could ever physically touch. There is a kind of freedom in that. Not the freedom of crossing every distance, the freedom of knowing what distance is. Science becomes a way of moving without moving. It cannot carry the body to every star, but it can carry understanding across impossible gaps. A telescope does not shorten the road to a galaxy. It receives what the galaxy has sent. A spectrum does not place a human hand on a distant planet, but it can reveal an atmosphere, a temperature, a chemical hint, a history. A radio telescope does not enter the deep universe, but it listens to waves that have crossed the dark for longer than civilization has existed. Knowledge is not the same as travel, but it is not nothing. It is one of the ways consciousness escapes local blindness. The universe may keep most stars beyond reach, but it still allows their light to arrive. That light is patient. It carries information through the void without needing our permission or our presence. It arrives as an old message, often from a world or star as it was long before the moment we receive it. When we study it, we are not conquering the source. We are entering into relationship with it. That difference matters. Exploration does not have to mean possession. It does not have to mean planting flags, building colonies, or turning every place into an extension of ourselves. At cosmic scale, exploration may become something humbler, the disciplined act of understanding what cannot be owned. The ability to accept that some places are real, meaningful, and forever beyond us. The trap, then, changes the meaning of Earth. If space were easy, Earth might feel like a starting point to be outgrown. A birthplace, perhaps, but not a destiny. But once the scale of the universe becomes clear, Earth becomes something more. Not a prison in the simple negative sense. Not a cage to resent. A refuge. A rare, habitable island inside a universe that is mostly indifferent to breathing creatures. Earth gives what space does not. Air that does not need machinery. Water that falls from clouds. Pressure that holds the body together. Gravity that shapes bones and balance. A magnetic field and atmosphere that soften the violence of space. A biosphere that turns sunlight into food, waste into cycles, chemistry into living continuity. The ordinary world becomes extraordinary when compared with the void. A forest is not just scenery. It is a functioning miracle of atmosphere, biology, water, soil, and time. An ocean is not just water. It is part of a planetary system that has remained hospitable across deep history. A breath is not just a reflex. It is participation in a world that space does not provide. To call Earth small is true in size, but not in meaning. Against the universe, Earth is a speck. Against the needs of life, it is almost everything. It is the place where fragile chemistry became memory, language, grief, mathematics, music, and curiosity. It is the place where matter learned to look back at the stars and ask whether it could ever reach them. Maybe that is why the trap feels so painful. We are made of the universe, but not free to move through most of it. The atoms in our bodies were forged through cosmic processes. The iron in blood, the calcium in bone, the carbon in cells, the oxygen we breathe. All of it belongs to a larger cosmic history. We are not separate from the stars in origin, but in travel, we remain deeply separated. Cosmic in substance, planetary in survival. That tension may define us more honestly than either optimism or pessimism alone. It is easy to say humanity will conquer the stars. It is easy to say we never will. The truth is more subtle. We may reach farther than we have. We may build machines that travel to nearby stars. We may send probes into interstellar space. We may learn to live for longer periods beyond Earth. We may find ways to extend our presence through robotics, artificial intelligence, or forms of exploration we have not yet imagined. But most of the universe will remain beyond us. Not because we failed, because the universe is larger than access. There is humility in accepting that. But there is also wonder. A thing does not need to be reachable to be meaningful. We cannot walk into the early universe, but we can study its light. We cannot visit most galaxies, but we can know they exist. We cannot hold a star in our hands, but we can understand how it burns, how it dies, and how its death seeds the elements of worlds. The unreachable still shapes us. It enlarges the mind. It gives consciousness a direction beyond survival. It teaches us that reality is not limited to what we can use. This may be the deepest answer to the title question. Space is a trap because its scale and laws create profound isolation. But awareness of that trap does not make life smaller. It makes life more precious. It makes every habitable surface more valuable, every atmosphere more delicate, every living world more rare. It shows that Earth is not merely beneath the sky, it is protected from the sky. It is the small island from which the cosmic ocean becomes visible. And perhaps that is enough to change how we look upward. The stars are not waiting just beyond our reach like lamps across a field. They are distant suns, some already beyond any possible journey, some visible only because their ancient light has survived the dark. They are not promises of easy escape. They are reminders that reality exceeds us. But they are also invitations to understand. Even if our bodies remain near Earth, the mind can travel by evidence. Science crosses distance through light, mathematics, instruments, and patience. It turns isolation into knowledge. It turns unreachable stars into subjects of study. It turns the silence between worlds into a question we can ask with increasing precision. The universe may keep the stars unreachable, but it still allows us to understand them from within our small island of life. That is not defeat. It is a different kind of exploration, a quiet one, a human one. We may never touch most of what we see. We may never cross the largest distances. We may never overcome every horizon written into space-time. But from Earth, under a sky full of old light, we can know that the trap exists. We can know why it exists. We can know that our longing for the stars is part of the same universe that keeps them far away. And in that knowledge, the world beneath us becomes less ordinary. The air becomes shelter. The ground becomes inheritance. The night sky becomes both boundary and message. Space may be a trap, but Earth is the reason we can understand the trap at all. Good night, and see you in the next video.